In this video, I would like to show you a beautiful, simple-sounding theorem from graph theory, which I proved in my thesis a few years ago. Even if you are not interested in this particular problem, it illustrates an elegant proof technique which might be useful to have in your problem-solving toolbox. The topic is motivated by a fascinating theory of expander graphs, which I don't plan to cover here, but maybe I'll make a video about them in the future. If you stick with me until the end, I will show you an open problem which might not even be that hard. Alright, let's get started. The theorem says that in every graph with n nodes, there is a small enough non-empty subset of its nodes without any unique neighbors. Let me explain it in an example. Here is a graph with 12 nodes. That means we are looking for a subset of at most 7 nodes. Let's pick some 2 nodes just to get familiar with the definition. Each node connected to one of them is called a neighbor. More specifically, I'll keep a count of how many connections each node has with the chosen subset. A unique neighbor is such a node which has exactly one connection with the subset. As you can see, this subset of 2 nodes has 9 neighbors, 7 of them are unique neighbors, and 1 node is not a neighbor of this subset at all. While this subset does not satisfy the condition from the problem statement, we can add 3 more nodes to it. The subset will still not have more than 7 nodes, and will no longer have any unique neighbors. To recap, the theorem says that we can choose at most about a half of the graph nodes, potentially adding 1 extra node, in such a way that all other nodes are either connected to them at least twice, or not connected at all, but not just once. Before I get to the proof, I want to encourage you to pause the video here and play with the problem yourself for a moment. If you come up with other approaches, I'll be very curious to discuss them in the comments. Okay, let's think about how can we prove that in every graph we can find a small subset of nodes with no unique neighbors. Well, we need to build a non-empty subset. Let's start with a single arbitrary node. That one will most likely have some unique neighbors. How can we expand our subset to get rid of these unique neighbors? There are 2 options. First option is to add the unique neighbor to the subset. However, that's not a very good idea, because that way we are likely to gradually add most of the graph nodes eventually. Much better way is to keep that unique neighbor excluded from the subset and instead add to the subset one of its neighbors, which is currently not in the subset. That way, this node will already have at least 2 neighbors in the subset, and if we only keep adding nodes, it will never become a unique neighbor again. This is actually quite a promising idea, but you can probably already smell some problems with this approach. First of all, what if the node which is currently a unique neighbor does not have any more nodes which are not in the subset? And we just need to add this node to the subset itself. Secondly, we might actually end up adding a node that we previously worked hard to build up its neighbors to make it a non-unique. An extreme example where this approach is inherently flawed is a star graph. If we end up starting with a central node, there's no other way than eventually adding all of its nodes to the subset to ensure there's no unique neighbors. My proof starts with a bit of a trick. Start with finding a maximal matching. That means pairing up some connected nodes such that every node is matched with at most one other node. By maximal, I mean that there is no matching that would pair up more nodes. Note that we don't actually need to know how to find that matching. It is sufficient for the proof that the maximal matching exists in every finite graph. Next, you consider 2 possible cases. Either the graph contains a perfect matching, meaning that every node is paired up with some other node. In this case, you can pick any match to start with and add both of its nodes to the subset. Then, we use a very similar approach we discussed earlier. At every step, we pick a unique neighbor and add its match to the subset. This might create some unique neighbors, Therefore, we continue until there is no unique neighbors left. Notice that at every step of this algorithm, both nodes from a match are either both unselected or both already resolved. So this way, we end up choosing at most one node for every match, plus one extra node for the initially chosen match. Alright, this covers the graphs with a perfect matching. But what about the graphs that do not have a perfect matching? In these graphs, after taking a maximal matching, there are still some nodes left unmatched. Let's start with any one unmatched node. Then, we continue in the very same way as before. In every step, we take a unique neighbor and add its match to the subset. We keep this algorithm running until there are no unique neighbors left. In the end, same as before, we only select at most one node from a pair of matched nodes, plus an extra one for the starting node. Actually, let's be a bit more careful. There's a potential problem. Remember, in this case, there are some unmatched nodes. It would be quite inconvenient if one of the unmatched nodes became a unique neighbor at some point, because it wouldn't have any match that we can add to its subset. Here comes the beauty of this proof. Such a situation can never happen. If it did happen, we can shift the matched edges along the path to the starting node and create a larger matching by adding one more match to the newly discovered node. That would contradict our original assumption of the maximality of the matching. Therefore, it can actually never happen that we would discover an unmatched unique neighbor. The original algorithm works without a need for any modification. Let's recap how this algorithm proves the theorem. For any graph, the algorithm finishes because in every step, it adds one node to the subset and there is a finite number of nodes. Also, it never adds both nodes from the same match to the subset. Altogether, it finds a subset of at most n½ plus 1 nodes, without any unique neighbors. Because this algorithm always finds such a subset, it inevitably means that in every graph at least one such subset exists. There might be more valid subsets. There might even be much smaller subsets, but there certainly is at least one such subset. Finally, here's the promised open problem. I speculate that the stronger version of the theorem is also true. Does every graph has a small subset without any odd neighbors? Intuitively, an odd neighbor of a subset is connected an odd number of times. Do you remember this graph from the introduction and the small subset of its nodes without any unique neighbors? The same subset actually has some odd neighbors, but I guarantee you that you can find another small subset which does not have any odd neighbors. I hope you learned something new today, got inspired, and leaving with a problem to think about. Last, I would love to give a big thanks to Grant Sanderson for inspiring me to create this video, and to the Manim community for expanding Grant's ideas and building the animation tool that I used here.